Welcome to Yaka Digital Network. In engineering, designing a part is only half the job. You also must ensure that the part survives its operating environment. Before we protect a material, we need to know how it fails. The three primary threats to any design are mechanical wear, galvanic corrosion, and the most common enemy of ferrous metals, oxidation, commonly known as rust. Look at these local corrugated metal roofing sheets. The brown patches show exactly where environmental moisture and oxygen are beginning to compromise the unprotected steel. This cross-section shows the mechanics of that failure. When ferrous metals like iron and steel are exposed to oxygen and moisture, they form iron oxide. Unlike some chemical reactions that seal a surface, rust is porous. It flakes away, continuously exposing fresh metal underneath to the elements. Because this degradation is a continuous cycle, failing to apply the correct protection is an active choice to let the structure eventually fail. When we scale up to large outdoor structures, like these steel electrical transmission pylons, the metal faces constant rain and air. A highly robust surface coating is required to prevent immediate oxidation. The standard defense is galvanizing, coating base steel with a continuous zinc layer. If scratched, the raw steel underneath is exposed to moisture. Here, zinc acts as a sacrificial anode. It proactively corrodes itself, leaving the exposed steel completely untouched. True environmental protection requires engineering a chemical sacrifice. We let the coating erode so the core structure can survive. Internal moving parts face an entirely different threat. Inside the engine and gearbox of a commuter taxi, components operate in a high-stress, high-friction environment. Engine gears face a mechanical paradox. They require extreme surface hardness to withstand constant friction against other metal parts. But if you harden an entire solid steel gear, it becomes highly brittle and will shatter under sudden impact. This thermal map shows case hardening. Introducing carbon into the steel's surface at high temperatures, followed by rapid cooling, creates two distinct physical properties. The glass-hard outer case resists daily wear, while the ductile flexible core safely absorbs sudden shock without snapping. Mechanical defense requires altering the molecular structure of the material. The protection is engineered directly into the physics of the part. As a draftsperson, you don't draw these invisible chemical and thermal layers. You must explicitly annotate them using standardized technical language. Global treatments are placed in the general notes section of your title block. For the pylon, you write, Finish, hot dip galvanized to ISO 1461. For the engine gear, you specify surface treatment, case hardened to a depth of 0.5 millimeters. Let's test your understanding. Pause the video. Imagine you are drafting an aluminum window frame exposed to severe weather. What is the correct protection method, and how do you write it as a note? A perfectly engineered chemical solution is useless if you cannot accurately communicate it to the workshop technician manufacturing the part. Welcome back. Because aluminum naturally forms a protective oxide layer in air, the correct method is an electrochemical process that thickens that layer and accepts dyes. The answer is anodizing. In your title block, you specify Finish, anodize. Here is a final summary matrix mapping components to threats, protections, and drafting notes. Outdoor steel gates face rain and rust, so we galvanize them. Engine gears face friction, requiring case hardening. Bicycle handlebars face sweat, so we specify chrome plating. Mastering these specification methods ensures your theoretical designs survive the harsh realities of the physical world. Thank you for learning with Yaka Digital Network. See you in the next session.